Okay, hopefully it's recording. I have no idea where it's gonna save the recording, but let's get started. Uh, we're gonna crash course batteries today. Like, batteries are hard. I've spent quite a bit of time working on them, and our goal today is to understand why the Mark 6 battery is the way it is. That way, you all can make good design decisions for Mark 7, and so that like people who aren't on accumulator understand what's going on with the battery. And so I'm gonna try to start from like ground zero, where everyone just has basic ISIM knowledge, and work from there to explain how our battery works. The challenge of building a race car is to get energy from a storage system into the ground to accelerate the car in the most proper direction at all times. We want to be accelerating, right? That was something that was covered in one of the early lectures I gave in onboarding, where our goal is to be accelerating in the proper direction as much of the time as possible. And in like a gasoline powered car, your storage system is the gasoline, and you're converting the energy in that gasoline into a force that you put into the ground to accelerate your car. We care about an electric car because we're building an electric car. And so our energy storage system is going to be some sort of electrical energy. And so the equation for power in electrical sense is I times V, which is current times voltage. And so we either need to have a really high current and or a really high voltage in order to get that power. So we want to feed as much power as we can legally into the motor, and then that can put that power into the ground, which would then allow us to accelerate in the most proper direction as much of the time. One of the things with power is there are inefficiencies with it. And with an entire electrical system, right, it's not perfect. You're gonna lose energy. And so the power drawn by a resistor is I squared R. The wires in our car have a resistance. And so in order to minimize the power losses due to heat, right, P equals I squared R tells us the amount of heat that will be generated by a resistor that's not doing any work. We need to reduce I as much as possible because we can't change the resistance of the wires, right? Let's say our wires are the same length. The main thing we can change is the current draw. And if P equals VI, then our goal is to maximize V and minimize I. That way, the losses that we have between the battery and our motor, or however we're getting into the ground, are minimized so we can have the most efficient car. This means we are trying to maximize V as much as possible. That's why we have high voltage everywhere, right? We could run a low voltage car, but that would mean that we would need really, really high currents, and we'd lose a lot of energy through the losses in the system. And that's also why a lot of cars that are EVs outside of formula also run on 400 volts, and the latest models of Tesla and Lucid run on 800 volts, because the higher they get that voltage up, the lower losses that they have. So let's take a look at what are battery cells. So here's an example of two battery cells. Right here, you can see there's a positive terminal. That's one connector. And then on the back side, you have a negative terminal. And over those two, if you touch one and touch the other with a multimeter, it'll tell you that there's a voltage between the two of them. And so there is a chemistry inside the battery that is allowing there to be that voltage potential across the two terminals. And that chemistry is determining what that voltage is going to be. There's some other characteristics to a battery cell that really matter to us, which is like the capacity of the battery. How much energy can we store in amp hours or watt hours? The C rating, which is how much we can safely draw from the battery at any given time. And batteries also have an internal resistance. So that I squared R stuff we were doing with the battery, with the wires, also applies to the batteries. The more current we draw, the more losses we're going to have from the battery, the more heat the battery is going to generate, potentially overheating the batteries. And that's a problem that we'll talk about in a few seconds. But anyone have any questions about these like four main characteristics of the battery? The chemistry determining the nominal voltage, the capacity, the C rating, and just how internal resistance can play into that. Yeah.
It's like the same current draw, the C rating.
Yeah. So I might have a battery that's rated for 3000 milliamp hours. So that means that it can have 3000 milliamps drawn from it for an hour. The C rating tells me how much quicker I can draw that. So if I have a C rating of like 30, that means I can draw 3000 milliamp hours times 30, or 3000 milliamps times 30, which would be 90,000 milliamps, right? Yeah, 90,000 milliamps. I can draw that for however much less time. If I have like a 60 C rating, I just multiply the milliamp hours by that C rating, and that gets me the safe discharge of that cell. Yeah. Any other questions? You had your hand up.
So by like, for example, the 90 milliamps per hour, does that mean like you can keep sustaining that, like keep it burning at that pace for like many hours? Or does that mean like once that hour is like it will be like dead?
So if you have the capacity on the battery, right? Like let's say it's a 3000 milliamp hour battery, that means I can draw 3000 milliamps for 1 hour and then the battery's dead.
I see.
But now if I'm drawing 90,000 milliamps, I can't draw it for a full hour because the capacity is only 3000 milliamps for an hour. And so I would have to divide the 1 hour by 30 because, right, I'm drawing 30 times the initial capacity. And so I would only be able to draw the 9000 milliamps for 2 minutes.
Let's see, what's the fastest, like maximum power
Exactly.
at the sake of like.
Exactly. Yeah.
For our new cells, do we have to do testing and determine our C rating and stuff like that, or do they have it already?
So these are all a part of the data sheet. We'll talk a little bit more about why we do single cell testing, and how that ties into the decisions we make on the car for batteries.
What is the nominal voltage? Like nominal voltage is like.
Yeah, so depending on the chemistry of the battery, it will have a different nominal voltage, and that's like the average voltage that battery is going to be at. The battery voltage can be higher than that. You can charge it to higher than that, and it's safe. It can be lower than that, and it's still safe. But the nominal is like the average. It's the baseline voltage that it's going to be at. Yeah. Yeah. Great. So there's different types of battery cells. We are very accustomed to seeing the ones in the top left corner. Those are our cylindrical cells. We use those because they're really easy for us to source. We can easily get 2170 batteries. We can get 1865 batteries really easily. In the past, we have used something called pouch cells, which are like the ones found in smartphones. You can see in the picture on the bottom. They are a lot harder to source because there's so many different sizes and capacities and variations on different pouch cells. And the ones that we would want to use were both very expensive and we might not get them for 6 months. And so they could potentially put a stop on our car. And so just for that reason alone, we decided we don't want to do that. There's another type of battery cell called a prismatic cell. I have no idea how it works or what it does and how it's different from a pouch cell. But if you're interested in that kind of thing, we can do some research together and figure it out. So, okay, we've looked at the individual cell. Right now, how do we get to that high voltage and high current that we want this car to be able to draw for a competition? Well, we can put the cells in series and that will add our voltages together, or we can put the cells in parallel and that will allow for more current draw. Just like a capacitor, right? If you think of the battery like a capacitor, you put a bunch of capacitors in series, the voltage between the top one and the bottom one is going to be huge. Or if you put a bunch of capacitors in parallel, you're going to be able to draw a lot more current through those capacitors, because the parallel plates just become bigger. The thing to note as well is the total capacity of the battery that you make is the total number of battery cells you have in there. So if I have the capacity of a battery pack that has 9 cells in parallel is the same as the capacity of a battery pack has 9 cells in series. Because I have how many watt hours of storage in each cell. I'm just drawing it as more current or more voltage based on how I lay out the pack. And so these are some constraints that we are going to use to help determine how we spec out our pack. Going back to your question that you asked earlier, like how do we tell what the batteries are like? This graph is like a really, really cool graph to understand, and it's a graph that we as a team tried to replicate. And there's a lot of lines. Don't worry about these lines that are going from left to up to or bottom to top. Worry about these lines that are like swooping curves from the top left to the bottom right. What these lines are telling us are as we discharge the battery cell, this is the output voltage of the battery cell. And so these lines are at different discharge rates of the battery. And you can see initially there's a significant drop off, right? We drop about 0.1 to 0.2 volts, and then we flatten out, right? The gradient stays about flat, and then we drop off at the end again. And that's interesting because remember, we want to maximize voltage. Let's say I maximize voltage at this point, and now I run my car for a little bit. I'm gonna be down here. Let's say I have a bunch of battery cells in series. That's gonna add up at 0.1 to 0.2 volts of drop off at the beginning is gonna add up to maybe 2 to 3 volts, which could be a pretty significant inefficiency in the car. This is the testing that we do on our battery cells at the beginning of every year. At the beginning of every year, we do something called single cell testing, where we take our battery cells and we attach them to a DC load. And we charge them all the way up, and then we drain energy from them and see what the voltage is over how much energy we drained. The reason why we do our own thing is this graph can be significantly affected by a couple of different parameters, like temperature, like how we're discharging the battery cells, whether it's a continuous discharge or oscillating discharge, and a couple of other factors. I'm not 100% clear on exactly what we were testing in our single cell charging, but I'm pretty sure it had to do with this graph. And if you have more questions about that, you should reach out to Andrew P. But that's the graph that we're trying to go for. This was found in the data sheet. We try to grade a more accurate version of this, but from what I've heard, this graph was more than fine enough, and we didn't really need the single cell testing this past year. Yeah, this was in the spec sheet, and this is the spec sheet for the current batteries we're using on our car, the Samsung 40Ts. We can compare this graph for various different cells that we want to use and compare the capacities and the voltages to decide exactly what battery cell we want to go with. Yeah.
So, does the documentation require us to replicate that graph?
No, it does not require us to replicate it. We choose to replicate it to make the best design decisions for ourselves. And that is something that, as a team, we have decided to do, but we are not required to do. And so in the future, we didn't want to put effort into doing that, and we wanted to just use the datasheet graphs. I don't think that would be a bad idea. It's something that we should talk to Andrew and Mo about. Yeah.
Am I allowed to conceptualizing how the discharge capacity relates to the voltage?
Yep. So I have my battery cell, right? And I've used it a little bit. The voltage is going to drop a little bit. I have my battery cell and I use it even more. It's going to keep on dropping. And so as I keep on using my battery cell, the voltage drops. And then when I use it all the way up, it drops at the very end.
So the higher the discharge capacity is, the more it's the discharge.
Yeah, discharge capacity is how much energy you've taken from the battery. It's the amp hours of the battery. Yeah.
You mentioned something about like inefficiency, like at the first drop.
Yeah. Yeah, so you can see at the beginning, it's a lot steeper than in the middle. And so that means that the voltage over the very beginning, if we charge our battery all the way up, right? Like, let's say this is the battery, charge it all the way up. It's now like full. At the very beginning, I just pull a little bit of energy from it, but the voltage is going to drop a lot.
I see.
And that means that if that happens on every cell, my voltage of my overall car is going to drop a lot, right? If my max charge voltage is 400 volts, right? And I have 100 cells in series. So that means each cell's at 4 volts. And now it drops 0.2 volts per cell. That's going to be a 20 volt drop in the first very little of discharge. Right? And 20 volts is a pretty significant amount. That means that I would have to make up for that loss in current, which means I now have more resistive losses in my cables because P equals I squared R. Yeah.
So I have two questions. So from this graph, which voltages it make sense for us to charge our batteries up to?
Yeah. we have another limitation, so. Do I talk about it here? There's our other limitation. We have a 400-volt limit on our motor controller. So we can't put more than 400 volts on our motor controller. And so using both this graph and that 400-volt limitation and a couple other limitations that I'll go into in a second, we were able to decide what our pack configuration is going to be.
Second question, what's the 2.5 volt cutoff?
Yeah, I think they just stopped testing at
Oh,
2.5 volts. Yeah, because with the battery, when you get below a certain voltage, it goes into a state called deep discharge, where you can't charge it again and the battery cell is dead. And so we purposely keep our battery cells between there's a term called state of charge, which is the percentage of charge that the battery has. And we try to keep it above 30%. I believe that's when it starts going into deep discharge.
Should we also, I guess for this semester, we have our new cells. For this semester, should we also start with single cell testing?
That is something you need to talk to Andrew and Mo with, because we have the cells. Sure, we could use the single cell testing to figure out exactly what we want our pack capacity to be, but there's other parameters that go into pack capacity that are probably going to make more of an impact. Yeah. So picking our battery cells, we picked the 40T due to this curve looking pretty good. And by pretty good, meaning the drop off, that initial drop off wasn't too much and it didn't take up too much capacity of the battery after that initial drop off. So we didn't mind not charging it all the way and leaving that initial drop off there. They're really affordable and they're easy to get our hands on. So those parameters all made it very worth it for us to go with them. A couple of other things that we could have done with the battery cells that maybe in the future are worth exploring. There's various types of battery cells. So there's the 1865, and what those two numbers mean are 18 millimeters in diameter and 65 millimeters in length. So we're currently using 2170s, which are 21 millimeters in diameter, 70 millimeters in length. And recently it's become popular to use 4680s, which are 46 millimeters in diameter, 80 millimeters in length. We used to use 1865s. That's what we used on Mark V. We switched away from them on Mark VI because it would allow us to have less electrical connections to battery cells, since the energy inside of the cell, the capacity of the cell, is proportional to its size. So, like not linearly, there's some relationship, but it's proportional to the size. So because we're using a bigger battery cell, we didn't need as many cells, which means we needed less connections to the cells. In the future, we should look at 4680s. Right now, they're impossible to get your hands on because all car companies are trying to use it for their cars. But I think in a year or two, they should be pretty widely available for us to use as a team, and something that we should definitely consider, since they could make spot welding even easier. Like, look at how big that shoulder is for spot welding, and because it would again reduce the number of connections we have to battery cells, which then allows us to have less points of failure. Picking our battery configuration. So these are the two main parameters that helped us decide, or there's another parameter that I'm going to explain here. I forgot to include it here. First is we have a 400-volt limit on our motor controller. So even when our battery is charged up, we don't want it to be past 400 volts. And so in theory, if we look at this chart, 4.1 volts is the max, 4.2 volts is the maximum charge of the battery cell. That means that we don't want to have more than 400 divided by 4.2 cells on the car or in series. We decided that we're not going to fully charge our cells, which then allows us to, I think we assume 3.85 or 3.9 volts on our cells, and that's what we're going to charge them up to. The other parameter is 8.6 kilowatt hours to get through the endurance race. This number is magic. We don't know where it came from on the team. We don't know why it's this, and this is why we need a driving car. So then we can confirm this number or determine that it's overspec. I think it's overspec. Like, all my intuition tells me that 8.6 is way too high and we should be able to drop. But right now we have no data to prove that, and that's why it's imperative we get the car running. Yep.
What's the average? Just a car, like, well, I guess what's a maximum current draw?
Yeah, so one of the limitations that the rules gives us is we cannot draw more than 80 kilowatt hours. And so the maximum that we can draw is our voltage times our current multiplied to 80 kilowatt. A final parameter that we have is, according to the rules, we need to have 6 different segments to split up our battery cells, and I'll talk more about the safety around this in the next slide. But that means that, and these segments need to be in series. So any series count we have has to be divisible by 6. With all these parameters and a lot of thinking, we came up with our pack configuration of 102S 5P. You'll say 102S is bigger than the 400 volts because of, right, it's 4.2 times 102 is more than 400. And that's why we don't charge our cells all the way. Sure, we lose a little bit of capacity, but we have enough cells here that even that small loss of capacity doesn't make a difference. The other thing to note is, let's say we wanted to add a 6th cell in parallel. We can't just add that 6th cell to one group of series cells, right? Like if I have 9, I'm gonna do it on this whiteboard. If I increase voltage in this direction, so that means all my cells are in series in this direction, and all my cells are in parallel this direction. So this would be a 4. This would be a 4 or 5S4P pack, because I have 5 cells in series, 4 cells in parallel. I can't just decide that I want to add another cell in parallel here to increase my capacity. I would have to add another cell in parallel to every single point on there. And the reason why is if I add that cell in parallel here, that means that compared to every other series set, these 5 cells are going to be stressed less. And that's going to put additional stress on these other sets of 4 and lead them to discharge quicker. And they're going to hit the bottom end of that drop off quicker than these 5 cells. And so you don't even get you don't get the additional capacity of that cell. That additional capacity is just wasted. So, like increasing it to 102S 6P would add another 102 cells to our car, which is ridiculous. And so the easiest way for us to easily change the number of cells, so the capacity of our car, is to increase the series count. So if we make it 103S 5P, that only adds up another 5 additional cells instead of adding 102 additional cells. That makes sense, everyone?
Yeah, so there's 102 cells in series.
Yep.
Damn.
And the reason why we have 102 cells in series is we're trying to maximize voltage so we can minimize current, because the heat losses of power through a wire is I squared R. So if we reduce our current, then the heat losses are going to be reduced, which means that we were incentivized to increase our voltage as much as we can up to that 400 volt limit.
Is that also true that like the P will be equal to VI, but because it's an ice squared, which is like
Yeah,
it's portion of it.
exactly. Yeah.
So you don't charge them fully because we don't need to, or is it like another reason?
The 400 volt limit.
Oh, wait, yeah.
That's the reason why we don't fully charge them. Because sure, if our motor controller was an 800 volt limit, great, charge everything all the way. Like then we can get rid of 1 or 2 series sets, and that reduces the number of cells on the car if we still hit that 8.6 kilowatt hour goal. But because we have that 400 volt limit, we're incentivized to stay in this region of the graph where it drops off less than in this region right here. That makes sense?
Yeah, so we have like 408 volts if we charge everything fully. No, I don't.
Yes.
Yeah, okay,
Yeah.
so that's what we do.
That's why we don't charge everything fully.
That makes sense.
other things that we have to consider when making a battery are some of the safety considerations. There's something called thermal runaway. Yeah. I'll play the video. This is great. Yeah. Avery was way too happy when this video played. Yeah, he's the one who designed that battery pack that caught on fire. Anyways, thermal runaway is when there's a series of exothermic reactions that happen in the battery cell. And these reactions are a lot more likely as the battery gets hotter. And so if your battery heats up, it becomes more likely. And then let's say this happens, it then causes like some combustion, which then is more likely to cause it, and it spirals out of control and it goes into thermal runaway, causing that fire that was in the video. Exactly. Yeah.
Someone's car like last year, like they
Yes.
on some fire. Oh,
Yeah.
okay.
We don't want this. We are trying everything we can not to have this happen. And we have a lot of safety features that I can go into in more detail to prevent this from happening. But in order to prevent this from happening at a big scale, we need to prevent it from happening, from spreading, right? Like if one cell goes into thermal runaway, fine. How do we prevent that from spreading to more cells? And so we use something called different segments. So instead of having our 102 series, 5 parallel, all in one giant container, we do 6 smaller containers with a fireproof wall between them. That way, even if one of those 6 containers catches on fire, the rest are going to hopefully be isolated and not catch on fire and be safe. So limiting the amount of energy that is discharged. And that's what we refer to as our segments. Other things we do to prevent this is we have thermistors on each cell to measure the temperatures. And ideally, if the cells go above 60 degrees Celsius, which is way below their max operating temperature of 90 degrees Celsius, we just have a factor of safety built into there. If it goes above 60 degrees Celsius, we shut down the car. If one cell draws a lot of current, because the internal resistance of the cell, drawing a lot of current from a single cell will cause it to heat up very quickly. And so in order to stop it from heating up due to that high amount of current being drawn from a single cell, we have our fusible links that will fuse to prevent that cell from heating up even more. We have an active cooling system to cool off the cells. That way they don't have a risk of going to thermal runaway. And all these things go together to allow us to have a safe car. Yeah, right now we use some fans to pull air through vents, which then pull it through the car. I will have some pictures of it in a second. Yep. So, any questions on all of that? I know that was like a lot of weird physics and weird math and yeah,
What does a fusible links really do? Like they melt or something, like a fuse, and
yeah, they melt like a fuse if you draw too much current through
does it
them.
do like a circuit or with something?
It just breaks the
It
circuit.
just breaks it.
Breaks the circuit. Yeah, if you draw too much current through it, we've designed it so that it will break the circuit.
Why does fusible links testing take so much time? Because I remember it started last year, and it keeps going on and on.
I
Like,
swear.
I don't know, Anthony, why does it take so much time?
Asked, and like the time constraints are so stupid. Like basically, like there's 4 different levels of testing, and like
Yeah.
there's like time gaps between each level, so like you can't hit. There's one level where we just can't fucking hit.
oh,
It's dumb.
okay. That makes sense.
Time gaps and-
Yeah, like it's like you need it to flow within like 5 to like maybe 10 seconds, and then like it just there's some parts are just impossible.
they don't do
Yeah,
it.
yeah.
Yep.
So back on the slide about the exothermic reactions and the LED fire.
Yeah.
So, from what I can recall of AP Bio, exothermic is like a service out heat.
Yep.
So the fire just because there was so much heat and.
Yeah, and then it releases more heat because there was a lot of heat triggering the reaction, which then feeds back into itself and makes the reaction continue.
So it's not, it wasn't like a lithium fire, or whatever, just like a heat fire.
Well, the fact that it's a lithium fire is from the chain reaction is what is described as a lithium fire. Yeah. I think. Yeah. Tabitha?
That's your recipe, he said that like, when the lithium fire occurs, you have to like use water or something.
I don't remember we use a fire extinguisher, but Yeah. yeah.
It's come to any battery or?
So I talked about how different batteries can have different chemistries. We use lithium ion batteries. Those are known to have this potential. But something like a lead acid battery that might be in your car doesn't have this. Something like a nickel metal hydride battery doesn't have this. The thing with the lead acid battery and the nickel metal hydride battery is these curves look a lot worse.
Yeah.
You can't store as much energy in them and you can't draw as much current from them. And that's why a car battery, right, like weighs a ton, but the energy density is like really, really bad. And so it's a trade-off of safety versus having a higher energy density. Yeah. Any other questions on this part? Yeah,
Like, if we add one cell, why does it like reduce the load?
yeah. So I add one cell here, right? How much current can I draw from this? It's 40 times or 4 times the C value, right? So 4C, I can draw 4C from here, I can draw 5C from here, I can draw 4C from here, and 4C from here. That means from the pack, if this is my positive and negative terminals, let's say I try drawing 5C from here, these cells just won't let me do that. Which means I can only draw 4C from here. Which means that there's gonna be less load on these cells than there would be on those cells. Which means that as soon as these cells are discharged completely, I'm still gonna have a fifth of charge on all of these cells. And that charge is just wasted because I can't actually draw it. Anything else? All right, let's dive into the battery segments. These slides are from an interview I did, and hopefully that background will help you, but like, please feel free to stop me if this is a little too fast or too much. So like I said, we have 6 battery segments. These here are battery segments. 6 of them, and they go into our enclosure, which is that yellow box on the bottom. Our total pack config is 102S5P, and we use a 17S5P segment configuration because that's 102 divided by 6. The pack configuration is determined by the 400 volt maximum of the motor controller and the 8.6 kilowatt hour desired pack density, and 3.93 volts is what we charge to. That way we can stay under the 400 volt limit. And if you look at the graph and you look at where 3.93 is, the capacity, the amount that you can drain, is still greater than the 8.6. This was our Mark V battery segments. And you can see there's a lot of issues just from looking at it. There's wires everywhere. It's impossible to service. At competition, we dropped a screw into our accumulator, and there were open terminals that it shorted against, and the screw melted inside.
So the fans are mounted on some.
The fans were mounted on the segments, right? And so what are all these wires for? You have these black wires are for the fans. You have these wires to measure the voltages of all the cells and the thermistor readings. And you have so many of them just all over the place, which makes it impossible to debug. They did not take into account where the PCBs would be and how the connectors would go and where the wires would go. And that's why Mark VI is very meticulous about where the PCBs are going to be, where the connectors go, where the wires are go. And we've minimized as much wires as we can. The other thing that happened is these screws right here, those were terminals. They were charged, and that's where when we dropped the screw in, the screw touched 2 of those and melted.
Oh, shit.
Yeah, it was kind of bad, and we only covered them with Kapton tape. Kapton is not an insulator. And so we did not drive the car because of this. This was the reason the car did not drive. And so what did we do? we reduced the number of cell connections. That means that there were less voltages for the cells that we had to measure and less temperatures of the cells that we had to measure, right? If we go to 4680, we're gonna have even less cells to measure, which is gonna be even better for us. We moved the cooling fans away from the segments, right? On this, the cooling fans are mounted on top of the batteries. Underneath these fans are the battery cells. We move them away from the segments. We put them in the enclosure. That way, the enclosure will pull air over the segments and we don't have to worry about that. We also moved all of our electrical connections to the cell to one side of this, one side of the segment and did them all through a PCB. That minimized the exposed connectors that we have and made it so that like there's no large, the only large voltage drops are like from this cell to this cell, but you just have those little small voltage drops over each individual cell. There's just fewer exposed connectors because of that. One of the big issues that we ran into with this battery segment design was we initially wanted to mount the cells using a press fit. And so we went and got polycarbonate shop bought at FTC team and we press fit them in and you can see that it started cracking. And individual press fits would work, but when you have that many press fits together, it puts so much internal stress on the polycarbonate that like you can see how it's bending. And that's 1/4 inch polycarbonate. So those 85 press fits together led to failure, even though that polycarb is a very ductile material. So that's just to pack them in closer together. So you'll see that there's 5 cells in the vertical direction and 17 cells in the horizontal direction. We just offset them so then they could get packed closer in together, so we took up less space. Yep.
So if we're doing this again, then would a like normal kind of non-press fit have worked or did it have to be press fit?
We had to adjust it because the press fit didn't work, and I'll get to that on the next slide. But we found out the press fit didn't work, and this took us until March to find out. To figure out the solution to. Yeah. So how did we fix it? We used epoxy. So we drilled out all the holes in the press fits. We epoxied the cells in place. And then we ran into a couple issues with the epoxy because we didn't set up good jigs for us to install the cells with. And that is, you can see there's epoxy on the cell. If we're gonna attach a connector to that, the epoxy is gonna ruin that connection. The other issue that we ran into is you can see the variation in how deep the cells are, right? They're all different depths. And that's because we didn't have a good jig to make sure that they were all at the same height. These two combined led to pretty significant issues that we ran into with spot welding and attaching connectors onto the cell. We had to use a ceramic knife to scrape off all the epoxy. You remember this, right? Yeah, 3 hours. Andrew and Van spent at least 11 hours scraping epoxy off these cells. Right, like all that dirt just had to come off the cell in order for us to have a good connection. So now, how are we going to connect all these cells in series and parallel? The way we did that is something called wire bonding, or the way we wanted to do it was something called wire bonding, where we would have a wire be ultrasonic welded to the positive terminal and then to a pad on this PCB, that's the black thing. And then a wire welded the pad to the negative terminal on the next cell. And there's a robot that does this. It would be super fast, super easy. We wouldn't have to touch it. It would be good, except there were timeline issues with our sponsor, making this not valid for us. I would love to wire bond, but doesn't, like, we would then have to depend on a sponsor. That sponsor couldn't guarantee that it was going to be done, and so we had to look for other methods.
It was a PCB.
What? So the reason why we have all these connected to a pad, like a pad on the PCB, is because then we can now measure the voltages at every single cell location. And internally, one of the PCB traces connects to another place called the battery management system, which then allows us to monitor the voltages at each pad, which is really important for safety reasons that I can talk about after this. This makes sense? So because we couldn't wire bond, we switched over to a spot welding design where we cut these tabs out of nickel to spot weld onto the pads of the PCB and onto the cells. And so, right, the positive would spot weld to the positive tab, then onto the PCB, and then onto the negative tab. And we did FEA to figure out how much current can we draw through the tab to ensure that it would fuse at high currents, so that we don't draw too much current from a single cell. We had to use a nickel tab instead of using an aluminum wire because spot welding is a very different process than ultrasonic welding. And so we found that the chemical compatibility of aluminum, that was the testing I did with the K-Weld earlier, does not work with nickel. And so that's why we ended up making these tabs out of nickel and water jetting them. So in order to fabricate it, this was like all Rowan, this was all really cool. Initially we kept on burning through the negative terminals, and you can see them burn through there. And those holes could potentially make it so we have a bad contact and just overall not a good weld. And so we designed this 3D printed stamp to purposely lower the tab, so then it wouldn't be the spot welder that was pushing it down. It would be the like tab itself that was already lowered, and that significantly reducing damage to the tabs. Some of the other reasons we think that the tabs are blowing through is because you saw that Z height variation when we epoxied. We think that some of the cells that were sunk deeper were harder for us to get the welders down to, which then caused that. Or if there was dirt on some of the cells, that could have made it generate a lot more heat on the welding process, which would then cause it to melt. Cool things we did on the electrical side. So one of the things when you have high current, right, we're used to soldering everything, right? We solder stuff for ISIM, we solder stuff for high, pretty much all your classes you're gonna solder stuff. We can't use solder because we have high current potentially running through this. And if we have high current, that could generate a lot of heat, which would then melt the solder. And so then everything could become plop and accidentally short to something. So we use something called a cold welded connector in our terminals that connect to the PCB. And that's where we tried the nickel plating. That didn't work very well. We tried nickel plating these connectors to make them the right size because the initial ones didn't come out the right size. And that didn't work at all. But the way cold welding works is it's effectively a press fit, where because of the friction between the pins and the pins on the connector and the holes in the PCB, you create a welded joint between the two that ensures a good connection and doesn't change with heat. And so that's why we use those on the terminals for battery cells. The other cool thing we did is we used the M.2 connector that everyone's been talking about to attach the BMS, which is our battery management system, to our segment. That way, if we needed to replace the battery management system, we could replace it and not have to re-weld everything. What does our battery management system do? So our battery management system is a safety feature that pretty much all batteries that are lithium ion should have. And it does quite a few things. If you want to learn about it from an electrical perspective, talk to Melissa. But from a overall high level perspective, a couple things that it does is it checks it communicates with the thermistors to ensure that the cells aren't getting too hot, and it shuts down the car if they are. It ensures that the voltage drop, right? We have our voltages. We want these voltages to all stay the same. Otherwise, right, if this is 3.9 and this is 3.6, that could lead to issues because I'm not able to draw as much power from here, which then puts even more load and gets this into a deep discharge state. And so what it can do is I can draw current from this to lower it to 3.6, and that chip is responsible for that. So internally, remember how I was talking about we have those pads? Those pads have traces that are connected to the BMS. So the BMS can measure the voltage of every single set of parallel cells. And by having that as a quick swappable M.2, if there were problems with the BMS, we could just replace it out. Though, right now, the thing that has been an issue for us is we think we soldered this connector on incorrectly. And we think that there's some bad solder joints there, which has led to us getting bad voltage readings, which has led to us not being able to run the car. And so that's a little bit of context of where we're at right now. From a mechanical perspective, some other things we did on the segments is we have these pins. So, right, this is the accumulator. These pins prevent the segment from moving in X and Y. And so we can just drop the segment in, they land on the pins, and then the lid holds it down in Z and applies a pressure and locks the segment in place, so the segment can't move at all. And this was a really cool way to put the segments in, that way we don't need tools to lock the segment in place. I included the slide because it was a lot of manual labor to do all of this. We use a lot of different machines. In the future, you'll want to use the CNC lathe. But I spent probably 30 hours making standoffs for the segments.
Are the standoffs of the right, square ones?
All of these are standoffs except for the pins that I talked about earlier. These are all standoffs.
What is the?
What? It's the black plastic around the standoff. It allowed us to take our segment and put it down on a surface without destroying that surface. Because if I took an aluminum standoff and put it down on a surface, it might scratch up that surface. And so by putting the acetal around the aluminum, it's softer and it's not going to damage that surface.
Although, do you actually care if the wood of the table gets damaged?
Well, we also care about the material inside of the segment, or inside of the enclosure, right? We don't want to damage the enclosure. And so when we put the segment into the enclosure, we don't want to scratch it up.
Like where it's rubbing?
Yep,
Touching?
where it's touching.
That's it, for this one.
Yep. So here's where the acetal tubes are, right? And they locate on the bottom of on the bottom plane.
That's enough.
Yeah, this is this is the length of the accumulator, and this is the, yep, so, right, this is a cross section of the segment. You can see each of the battery cells very lightly. Yeah,
So because of the design of the pins and the lid that like kind of holds it in place shape wise, you don't need tools to, otherwise it won't do whatever.
yep. Yeah, and so then the acetal is this standoff right here, and that bottom standoff right there, and that prevents us from not destroying this aluminum bracket right here.
Did you prefer that cups like I've made to like make sure it could stand the tiny piece?
I did it all with hand calcs. Yeah.
Can you see this?
They're really simple hand calcs. You take the weight of the segment, and let's assume we're accelerating the car at 20 Gs. You now know how much force is being applied. Let's say that force is being applied onto this pillar. You know the cross-sectional area of the pillar. You know what the tensile strength of the pillar is, or the UTS of or the yield strength of the pillar is. Force over area, right? You have your force, you have your area. Yep.
And the strength is greater than the force.
Yep, exactly. Final thing that I think was pretty unique and cool about what we did was we have these bus bars. We're hoping to move away from this because this was pretty complicated, but it did work pretty well. And the way these bus bars work is they have the connectors that are cold welded into them, and they go into the connectors that are cold welded on the segment PCB. And they have two bars that can slide in and out with each other. That way, if the position of the segments isn't exactly what we think it's gonna be in CAD, we can slide them, lock them in place, and then they will always fit. The thing that we had to do is because we have a fastener in this, we have to make that fastener positively retained according to the rules, and we can't use a nylon lock bolt because it might get hot. So we have this clear piece of acrylic that allows you to see that this nut is a lock nut. And we have a clear piece of acrylic that lets you to see that this bolt is a socket head bolt. And then you can lock this all in place, connect it together, and that's what it ends up looking like. And that's how they're connected, so you have your positive terminal there, that goes to the negative terminal on this segment, which then goes to the positive terminal on this segment, which then goes to the negative terminal on this segment, positive there, negative there, positive there, negative there, positive there, negative there, positive there, and then this is the output. And this is the input. Or that's the positive output, and this is the negative input.
Why does it matter that you must run socket head? Just that so that you can.
We'll say we need a socket head on positively retained volts.
So it
Or
positive
hex, yeah, or hex head.
X works.
Yep. I wanted to end today on a couple things. We can do whatever you want. I have an hour after this, so. One is we can go to the LPB and actually see this stuff, because I think that would be cool to see like how it looks here and go there. The other is I'm happy to answer any other questions you have about battery stuff. And I wanted to end on this slide, which I put together for my Tell the Story class, which shows the different components of the battery, right? So we spent a lot of time talking about the segments today, but there is the enclosure, which is this entire yellow thing. And that's what keeps the segments inside of it. And if all the segments go into thermal runaway, technically the enclosure should keep it contained. Then we have the lid, which holds everything down. And in order for power to leave this entire thing, we have our service section. What our service section does is it makes sure, can the brake be pressed? Are the battery cells in the proper temperatures? It has giant relays to prevent power from leaving the battery unless all these checks or safety checks are completed. And so it has these terminals that connect into there, and then there's an output on the output connector on the battery that only allows power out if all those safety checks are completed. And then Tabitha, your MSB is there.
Yeah.
We have the bus bars that I talked about, and you asked about how we cool. We have fans that are mounted here. So air gets pulled in through this duct, down over the cells and out through this vent.
Is that duct like off the shelf?
No, we 3D printed. Yeah. How's the waterproofing going, Brittany? All right, what questions do you all have? What do you all want to do? Yeah,
I heard from a member that the things weren't like, it didn't actually. But like it works, but like not.
was this Bentar?
Yeah.
I don't know whether they actually worked. I wasn't told they didn't work.
Okay, which fans? Is it enclosure ones?
Yeah, like the ones that like,
Hold the segment in place. My guess is the segments can tilt, but they're still locked in place on the bottom.
like.
Yeah,
Not good
because
to
we
be
don't have any
honest.
supports on the top.
Would it have been good to consider limits, or is it like not really?
Probably good to consider it. We just didn't do it, and I think we're gonna be fine, but we can see.
What was the again?
That's a car.
The MSD are the bus bars.
Oh, why is it called a bus bar? That's like interesting. I don't know what's that. Okay, I don't know.
MSD stands for what?
Master switch.
No,
I like,
no, master switch box is,
I've seen
MSD.
other teams label it MS. Master switch panel.
n-
Wait,
yeah,
the box though.
that's the
So,
box. MSD, what is MSD?
Oh, MSD, oh, shit.
Yeah.
Service,
Switch.
service something.
Master service.
Master switch.
I don't remember.
Okay.
Where's that?
Oh,
It's
that's,
the bus bars.
Oh, okay.
Can I go back to the side of the bus pass?
and what else do they do? Like, it's like, I'm not so sure what bus bars do.
Yeah, me neither.
What?
I'm not sure what the bus bars actually do.
So I have all my segments that are in isolation, right? They have a positive and negative terminal on them.
Yeah.
But they're only 17S 5P. So how do I get the 102S 5P that I need for the entire pack?
Oh, and you connect all of them, oh, okay,
In
oh,
series.
those are the bus bars, those things, yeah.
Yeah, the yellow things are and the blue thing is the bus
Yeah.
bars that connect them in series.
Oh, so the connect all segments together.
Yep.
Okay,
So how, what did that assembly, like, what is the yellow and blue represent?
The yellow and blue are just 3 different parts.
Which part is it conducting, I guess?
The red part,
they're made of copper, right? Wait,
they're made of aluminum.
no, yeah,
Where's the
and,
red part?
What?
Where's the red part?
This red part right here.
and that's actually bus bar.
Yeah, and this is the, what it actually looks like.
I
Yeah.
have a question about, kind of just going back to the whole like current draw thing. If, so for my project designing feasible links, right? Basically, would I be looking, the whole point of this is not to blow up at our like normal operating currents, right? So would I be looking for the current of each of the individual cell to like attach to link or the whole?
Individual cells.
Okay.
What pins are those, oh, like fastening on the sides, like,
These are just plastic
oh.
pins that are used to hold it in place, yeah.
that's cool.
They're snap pins.
Oh, those are used on the firewall. Okay.
Yep,
So this is the bolt to hold the conducting aluminum
It's
together,
like nylon,
Yep.
or-
and then.
it's a
these two-
distorted thread nut,
oh, okay,
because we can't use nylock since there's high current there,
oh,
so it could heat up.
okay, this sort of product does not heat up,
Distorted thread nut can deal with heat, nylock's not.
oh, okay.
Yep.
Oh, because the plastic melts, oh, okay.
Exactly.
So does a conveyor typically just use this sort of thread?
I don't know. I don't know what thread it is. I think it's a standard fastener that we have as a team.
And then these two are the conducting.
Yeah, those go into the connectors that are pressed into the PCB. Do you wanna go take a look at a segment and take a look at the battery? Yeah, let's do that.
Those segments are properly seen, as it's not five,